All right, welcome to the second example in section 4.8. In this example, we're going to be looking at identifying or determining whether our function is even, odd, or neither. Now, we've associated even and odd with just the highest exponent in our polynomial up to this point. But there's also another definition that we need to look at, because when we start having polynomials that have multiple terms and different transformations, they may not always fit one of these definitions. So the first definition, if a function's even, what that means is that if we take our input and make it negative, that's going to equal our original function. So what that means is that if a function's even, if we take our input and switch all of our variables to negative numbers and then simplify our parentheses, and it still equals the same original function, it's an even function. Now, an odd function is one in which if we take f of negative x, so same thing, if we take our opposites of every input, that is actually going to equal the same thing as if we took the opposite of the entire function. Now, if you look at what these means in terms of transformations, what kind of transformation do we get if we take the opposite of our input? Yes, that's a reflection around the y-axis. So what this means, if we reflect our function around the y-axis and it's still equal to our function, that means that that our graph really didn't change at all. For example, if we have a function like this, that's x squared. If we went and changed that and made it negative x squared, so we're testing right now to see if it's even. So we changed our input to an opposite of x, but if we work this out, we end up with x squared. So you'll see that this x squared is an even function, because if we take the opposite, if we make all of our inputs negative, it's still going to equal the original. Now you'll notice an even function like this, if we flipped it around the y-axis, it's still going to look exactly the same. So even functions are symmetrical about the y-axis. Now, an odd function, you're going to see, let's say for example, we had x to the third power. So if we made that negative, if we did negative x to the third, when we go ahead and we simplify this, we end up with just negative x cubed. That's actually the same thing as if we just did the negative of our entire function. So x cubed is an odd function, and you'll see with an odd function we get behavior like this. A cubic function looks kind of like this. Now if we flipped this about the y-axis right here, you're going to see that everything would flip like that. So odd functions are symmetrical about the origin, and even functions are symmetrical about the y-axis. Now, sorry for all the drawing on here, I just wanted to give some quick examples. But for right now, our key points are an even function. If you take f of negative x, so if you change all of your inputs to their opposite, it's going to equal the original function. If it's odd, that means if you take the opposite of all the inputs, it's just the same as if you took the opposite of the entire function. So let's look at some of these right here. So for the first one, if we go ahead and replace x with negative x, we're going to get negative x to the third minus 7 times negative x. That ends up being negative x cubed plus 7x, so we distribute everything. Now, that's the same thing as if we just took negative times our original function. So that ends up being an odd function. So again, look what we did. We replaced both x's with a negative x. We simplified, and then we went and factored out a negative 1 right here. And we saw that replacing x with negative x is the same thing as just multiplying our entire function by negative. So that is an odd function. Let's look at b. Same thing. We replace x with negative x. So we get negative x to the fourth plus negative x squared minus 1. If we go ahead and simplify down these parentheses, we're just going to end up with x to the fourth plus x squared minus 1, which is equal to our original function, which means this is even. Finally, our last one, you're going to see that if we replace x with negative x, we end up with negative x cubed plus 2, which is equal to negative x cubed plus 2. Now, you'll notice that's neither the opposite of our entire function or our original function. So this is actually neither even or odd. Now, this is interesting because normally we would classify this as an odd polynomial because it has a degree of 3. However, for our true definitions of even and odd, this would be neither, because if we take the opposite of x, it doesn't give us either our original function or the opposite of our entire function. Okay, so again, remember we've got 3 different ways to classify functions. They don't have to be even or odd. Just like example C showed, they could be neither.